Hello and most welcome to 1239, and I'm so happy that finally system have come to this lecture, so I know where I'm presently at. There is no need for a retake. I will just continue where I left off, so you need to watch or listen to 1238 first, and I will have to add the environment is incredibly important. Here is a very solemn, I'm currently in a big hall here, the Mercado, or what you call it, the sales place in Hisingen. It is completely calm, there's no noise here, there's no interaction, and I come to understand more and more that lack of focus and concentration is what the classical model is. It has a special mindset, a special way of understanding, or maybe a lack of understanding. So I continue here. A second related objection is that by using this stratagem, it inverts the relation of physical science to mathematics and elides the difference between them. If mathematics is a storehouse of ideas about the ways in which pieces of reality may connect with one another, then physics in this account becomes the identification of each of these mathematical connections with a physical reality. It is, we argue in this book, a practice resting on a misguided view of the relation of mathematics to science and nature. A third objection, and the one that will be most telling to a scientist, is that at the end of the day, this approach evades the work of explanation. It subsumes the unexplained laws and initial conditions under a vast framework of possible variations of nature, all but a tiny number of attributed to unobservable universes and unknown states of affairs. We develop a third approach. Its working assumption is that the more promising way to explain the regularities, as well as the structure of nature, and so to the initial conditions of one real universe, is to explain them historically. This approach proposes that cosmology complete its transformation into a historical science. It seeks empirical support in the most important findings of the cosmology of the last 100 years. those that have to do with the history of the universe and that have been codified incompletely in the now standard cosmological model. Structure results from history more than history derives from structure. This third approach has many counterparts in the life and earth sciences, as well in the historical study of human society. However, unlike the other two approaches, it counts on few representatives in the history of modern physics and cosmology. It fails to explain away the factitious character of the universe, that the universe just happened to be one way rather than another. However, it vastly enlarges the field of causal inquiry. As a result, it suggests an agenda of empirical research that communicates with the major discoveries that cosmology has made over the last 100 years and continues to make now. The historical approach, as we here understand and develop it, makes use of each of the three chief claims of this book. It discards the fabrication of imaginary universes in favor of a focus on the one real universe and its history. It takes the reality of time so seriously that it refuses to exempt either the basic structure of the fundamental regularities of nature from susceptibility to change. It wants to put mathematics in its place as an instrument of physical theory than as a substitute for it. Such an approach raises daunting problems. I have already touched on two of them in this early stage of our argument. The first problem is that if there is only one universe at a time, we must conceive the seemingly paradoxical endeavor of developing the science of a singular unity. The traditional way of avoiding this problem in cosmology is to scale up, to extend explanations developed to address pieces of the universe into ideas about the whole universe. In the cool-down universe, with its discriminate structure, exhibiting laws and symmetries, such pieces of the universe, for example patches of space-time, come in multiple instances conforming to the same regularities. Cosmology relies on the amalgamation of theories about local phenomena. However, scaling up from piecemeal theories of nature to cosmological conceptions, at least insofar as it relies on a distinction between stipulated initial conditions and unchanging laws, deserves to be resisted. It is just what the argument against the first cosmological fallacy and its Newtonian paradigm, an argument developed later in this chapter, forbids. We must face, without the relief that this procedure offers, the difficulty that the universe, as a reality both unique and historical, presents to science. Aristotle's conundrum about the ineffable character of individual being. The second problem is that if everything in this universe, including its regularities and its structure, changes sooner or later, we cannot accept a move that has helped define the path taken by physics and cosmology, at least since the formulation of special and general relativity, and of quantum mechanics in the early 20th century. The move is to combine a denial of an absolute background of space and time, distinguishable from physical events, with a reaffirmation of belief in a permanent structure of ultimate constituents of nature and in an immutable framework of laws and symmetries. The rejection of these twin ideas require us to change our view of causality and of the relation of causal connections to the laws and symmetries of nature. The selective realism of mathematics. The third central idea to our argument is a conception of mathematics and of its relation to nature and to science. Mathematics, according to this idea, represents a world eviscerated of time and phenomenal particularity. It's a visionary exploration of a simulacrum of the world from which both time and phenomenal distinction have been sucked out. Our causal explanations are steeped in time. The causes precedes the effect. If time were illusory, so would any causal nexus be an illusion. On the other hand, however, if time were real and inclusive to the point of resulting in the immutability of the laws of nature, our causal judgment would lack a stable warrant. Our conventional ideas about causation are confused. They assume that time is real, but not too real. The relations between mathematical and logical propositions are, however, timeless. The conclusion of a syllogism is simultaneous with its premise. They are timeless even though we reason them through in time and use them in the analysis of events in time. In the philosophical and scientific tradition within which the ideas of the singular existence of the universe and of the inclusive reality of time have remained decisive, mathematics has gained a power that none of the well-known positions in philosophy of mathematics seem adequately to explain or to justify. The laws of nature appear to be written in the language of mathematics. But why? And with what significance? The unreasonable effectiveness of mathematics remains a riddle without a convincing solution. In the history of philosophical ideas about mathematics, two sets of conceptions have come close to exhausting approaches to the solution of this riddle. According to the first set, mathematics is discovery of an independent realm of mathematical entities and relations. According to the second set, mathematics is an invention, made up conceptual entities manipulated according to made-up rules of inference. The problem is that neither of these approaches to mathematics seem to help explain the applicability of mathematics to the world. We propose a different view, one that begins from the acknowledgement of the contrast between the temporal character of every causal nexus and the timeless quality of mathematical and logical relations. Mathematics is about the world, viewed under the aspect of structured wholes, and bundles of relations, disembodied from the time-bound particulars that make up the actual world. Effacement of particularity goes together with denial of time. The world studied by mathematics is not quite our world, the one real world, soaked through and through in time. Neither, however, is it another world of eternal mathematical objects. Separated from ours by an unbridgeable gulf, it is a proxy for our world, a counterfeit version of it, a simulacrum, distinguished from it because in it everything is denuded of placement in time and phenomenal particularity. It is as if our mathematical and logical reasoning represented a Trojan horse placed in the mind against the recognition of the ultimate reality of time and difference. However, its selectivity, its disregard for time and particularity is the source of its usefulness. instead of regarding our faculty of mathematical and logical reasoning as a way of overcoming the limits of our natural constitution, we should understand it as a part of that constitution. By enabling us to expand and recombine our ideas of how pieces of the world can connect with other pieces, independently of particulars of any given time-bound circumstance. This faculty vastly enhances the scope of our problem-solving capabilities. It conferred an evolutionary advantage when we were simpler than we now are, and continues to confer one now that we have become more complicated. The foundation of this advantage lies in its simplifying approach to the one real natural world, rather than a direct access to another world of timeless and therefore unnatural objects, or to an array of possible worlds that never wore the garment of reality. It is a natural faculty that has nature as its subset. Nature as its subject, sorry. However, it increases its power by virtue of its distinct approach to the particulars of this one time-bound universe of ours. In its early stages, the relation of mathematics to the world of temporal change and of phenomenal particularity is direct, less by induction than by what Peirce called abduction, an imaginative jumping off from an open-ended series of particulars. Soon, however, the predominant relation of mathematics to nature becomes indirect. We begin to expand the range of mathematical ideas by analogy, without license or even provocation from natural experience. We go, for example, from the three-dimensional space of Euclidean geometry, with the simplification of our sensual experience, to geometries that have no counterpart in our perception. We move from natural integers by which we count things in the world to numbers useless in counting anything we will ever directly encounter and experience with our senses. Well, how true. I think he really puts in the knife where the incision needs to be made. If it were put somewhere into the side, it would not have been as decisive as it is now. I think it's absolutely amazing. This is one of the most interesting things I've read in a very long time. I'm sorry about my rather monotonous voice, but I'm trying really to get into it at the same time while reading it. Really to calm down the system, because a flustered and stressed system will not yield an understanding of these things. This is our background, he's pointing out. There's something almost impossible to discern because it's so mixed up and molded and obliterated. Distinction is obliterated. But here, one of the greatest account of what is real and what is somewhat less real. It's a scale also here. I say thank you very much. Thank you for your extraordinary patience, which is needed here. And I will continue with this in the following sections. This was the end of Heidegger 1239. Thank you so very much.